Okay students, so next topic is area vector and an electric flux. Till now we have treated area as a scalar quantity, but now we are going to introduce it as a vector quantity. Now why there is a need of treating area as a vector quantity? Because in some of the derivations it was found convenient to prove or write area as a vector. Now if area is a vector quantity, it needs to have some magnitude and a direction. Now magnitude is very clearly, if I'm having, suppose I'm having a figure over here, so magnitude of any of the area, suppose A, B, C, D, can be length into breadth, right? So this surface area we can find out the magnitude as we do for the scalar quantities. But now if we need to find out its direction, so the direction by convention has been decided to be perpendicular to the surface, right? Now if we are having any closed figure like this, A, B, C, D, E, F, G, H, so this is a cuboid, I can say. So now if we are having any closed figure, then the area vector of any of its side can be expressed as, the magnitude can be expressed as A, B, C, D, the area of this, that will be its magnitude. Next is to find its direction. Now we can have two perpendiculars on this. One is outwards and one is inwards. Now by convention it has been decided that the area vector will be having a direction in the outward direction, right? So this will be the direction of n cap and this is not taken, right? So I hope this is clear to you all. Whenever we are having a closed figure, the direction of area vector will be always perpendicularly outwards. It will never be inwards. Next is electric flux. Electric flux over any area in an electric field is a measure of the number of electric field lines crossing this area. I can show this with the help of some activity. In this activity, we will be taking some source of light which we'll assume as electric field lines, and then we'll be having different shapes and different areas. We'll see that the number of field lines which are crossing that particular area is different for the different areas. I have taken three different shapes, say rhombus, kind of spherical, circular, and one square shape, right? Now I have taken one torch which will be acting as a source of light, and this light I'll be taking as the electric field lines, right? So the light travels in a straight path, so we'll assume that it is a uniform electric field. So I'm just placing it nearby, and we'll take the shadow of each of this circle, each of this shape. Say the first one is this rhombus. You can see the shadow like this, right? Now if I am turning this shape, the shadow is getting different, right? So the amount of light which is allowed to pass through this particular area, this rhombus area, is different with the different inclination also. Like if it is standing like this, then the number of lines passing through are different. If I am tilting it, then the field lines are changing, right? Similarly, for the different shapes we can have, say if I am having this shape, the number of lines will be different. If I am having the smaller area, then the number of lines will be smaller. So now with this activity, we have clarified that the number of electric field lines crossing a unit area placed normal to the field is the measure of the strength of the electric field at that point. So this strength is known as the electric flux. Now clearly electric flux depends upon the area in front of the electric field lines. So if suppose we are having, say I'm drawing 4 electric field lines and this is the area, any of the shape I have taken, say A, B, C, D, then the number of field lines which are crossing through this area are 2. So this is the strength of the electric field crossing this area. Now if in the same field, the same area A, B, C, D, I'll just tilt it a little bit. Suppose I'm inclining it to this, then only one electric field line is passing through that same area. So that means the number of electric field lines crossing this area element is proportional to electric field intensity also and the surface area also, and this combination is known as the electric flux. So if I have to find out for the small area, then I'll say the small flux is denoted by phi, then it will be the electric field lines dot product with the area vector. Now area is considered as a vector, so we will be taking and the dot product over here. So it is E delta S cos of theta, because dot product when it is open, it becomes cos theta. So now the angle at which it is tilted, it is placed, is also important along with the surface area. One thing is, if we are having different surface areas, then the flux will be different. But if the surface area is same, but we are making it inclined to the electric field lines, then at what angle it has been inclined, it also matters in finding out the flux. So that means flux is a situational thing. Now what kind of electric field we have placed, what kind of area we have taken, and what angle we have taken that area, that will lead to the electric flux, right? So electric flux over a closed surface can be positive also, negative also, and zero also, right? If we take theta less than 90 degree, if we take theta greater than 90 degree, or if we take theta equals to 90 degree. So corresponding to these values of theta, flux can be positive, negative, or zero. Now what are the units of flux? Units of electric flux are unit of electric field and unit of area. So we can say that the SI units are Newton per coulomb multiplied by meter square, right? So it becomes Newton meter square per coulomb, right? And similarly, you can find out the dimensional formula. So the dimensional formula is, you can just find out M1 L3 T minus 3 A minus 1. So this is the dimensional formula. So this is about the electric flux.